Hi, I am Mingmou from Nanjing University. I am glad to give you this talk today. The talk is about succinct filters for sets of unknown sizes. This is a joint work with Yitong from Nanjing University and Huacheng from Princeton University. At first, I would like to explain the terms in the title. Maintaining a set of elements is a classical problem. One example is the dictionary problem. It requires us to maintain a data structure supporting two kinds of operations. One is inserting a new key, and a value is associated with the key. Another is return the value with respect to some key. We don't study the delete operation in this work. Filter is one of the most popular approximate variants of the dictionary problem. The problem asks for a data structure supporting first, insert a new element. Second, check if an element has been inserted, and a small false positive rate is allowed. In this work, we study the succinct data structures. A data structure is called succinct data structure if the space cost is close to the minimum space to store the database. For instances, the minimum space for dictionary is this. It is the entropy of database. The minimum space for filter is n log 1 over epsilon. It was proven by Carter et al. In 1978. In the setting of unknown sizes, the final size of the database isn't known in advance, so the space cost of the data structure has to depend only on the current database size over its lifetime. One example is the red-black tree. One counterexample is the dynamic perfect hashing. To succinctly maintain sets of unknown sizes with constant time in the worst case is obviously fundamental and interesting. In practice, we usually don't know the final size of the database, and such kind of data structure saves space. On the other hand, constant worst-case time is highly demanded in many applications. In TCS community, Pei, C3.F, and Weder were the first to study this problem. In their seminal work, they proved a lower bound for the filters and provided two data structures. One data structure is very close to be succinct, but it has amortized insertion time. Another data structure has constant worst-case operation time, but it uses linear space. PSW left an open problem. They asked that if there is a space and time-efficient data structure for filters. In this work, we present such a data structure that simultaneously enjoys the best of both worlds. In fact, the space complexity is even better than what PSW expected. In this work, we provide data structures for filters and dictionaries. Both of them are succinct and has constant worst-case operation time. In this talk, we focus on the succinct filters. Before presenting the data structure, I would like to introduce the computational model. Our memory model is called Extendable Arrays. For convenience, one may think everything is stored in the vector in C++, the array list in Java, or the list in Python. All the operations can be done in constant time. I assume you guys are quite familiar with at least one of these built-in data structures, so I'm going to skip this part. Previous works used the extendable array model. Raman and Rao presented a data structure for succinct dynamic dictionaries in this model. The previously mentioned data structures are also based on this model. we need a pointer to maintain an extendable array. Every record in the same array has the same size. So, an extendable array of length n and the record size r bits uses OW plus NR bits, where the W is the word size of our computer. Similarly, a collection of extendable arrays has space usage of this. In the rest of the talk, I will assume the word size is log n, and any data point fits in constant number of words. To make things simpler, I assume computation is free except memory access. First of all, the technique overview. Let's compare our solution with PSW. Both solutions solve the field problem by reducing it to a problem named Prefix Matching. PSW solves the prefix matching by further reducing it to the membership. In contrast, we solve the problem directly. PSW's solution introduces O n log n bits of redundancy in both of the first two steps. With the simple observation, we save the space loss down to O n log u bits. Finally, PSW solves the membership problem with a variant of B-Trie, which was introduced by Raman and Rao in 2003. It has amortized operation time, since the B-Tree is rebalanced by rebuilding. We introduce a succinct membership data structure. It turns out that our data structure solves the reduced prefix matching. Again, let's compare our solution with previous works. Arbitman, Nauer, and C3.F presented the first succinct membership data structure in 2010. Later, Burcha and Even refined the data structure to maintain multiset. Both solutions adapt the idea of sub-data structure. ANS deal with the overflowing with an auxiliary data structure. In contrast, the overflowing is not a problem in our case, since we may adjust the size of sub-data structure. The critical component is how we access the data points in sub-data structures. ANS randomly stores data points and equipped every data point with a pointer to access it. The pointer uses log n bits because they are log n data points in any sub-data structure. In order to reduce the space usage, we develop an idea of data block. One may consider the data block as our main technical contribution. We get the data points into log n groups. Every group is stored orderly. We name the tiny structure data block. So, to access a data point, all we need is the index of the data block. Hence, we spend at most log n bits on every pointer. Now, outline. At first, I present the succinct membership data structure. To make things simpler, I will assume the data points are uniformly sampled from the universe with replacement. The problem is reduced to a succinct membership problem with capacity, but the space usage depends on the size of the database. Then, we show the data structure solves the prefix matching under spatial input distribution. Finally, we reduce the filter problem into the prefix matching. We apply the standard double-full method. At any moment, we maintain two data structures, one with a two-fold capacity of another. We always insert the new data point into the larger data structure. After each insertion, we migrate one data point from the smaller data structure to another. If the smaller data structure becomes empty, we create a new data structure. The capacity of this new data structure is twice as the larger data structure. For example, the third data structure may contain the first 7 data points over its lifetime. In order to answer a query, we query both data structures. Our data structure with capacity uses O(n log 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 n plus m bits of redundancy and has constant worst-case operation time. For simplicity, I will assume m and n are in the same order and they are at least U2 0.001. Let's review the computational model. In this model, the data structure is represented as several extendable arrays. Since the data structure is succinct and we have only constant worst-case operation time, the new data point almost has to be stored in the end of one of the extendable arrays. To answer the queries, we need a navigation structure to help us retrieve the relevant data point. If we try to uniformly distribute the data points into n over log n extendable arrays, then, with high probability, every extendable array contains theta log n data points. So, every data point needs pointer of log log n bits. Note that we actually store the order of insertions with the pointers. It is exactly how previous works get done. However, a succinct filters for sets of unknown sizes can't afford redundancy of n log log n bits. The key notion is we don't have to store the insertion order. Instead, we can store data points orderly and succinctly. But we can't keep the data points sorted. It is too expensive. A data block has size log n over log log n. So, we reorganize unsorted data block into a sorted one as long as it is full. In conclusion, they are n over log n extendable arrays. With high probability, every array contains O log n data points. Every extendable array consists of O log log n data blocks. So, every data point equips with a pointer of log 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 n bits. We use log U over n plus log 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 n bits to represent a data point. I will elaborate this later. The description of the data structure consists of 4 parts. At first, we elaborate the data block. Then, we show how to answer queries, assuming there is no insertions. Next, we deal with the insertion, assuming reorganization is free. Finally, we show how to reorganize the data blocks. Here, we have the fully functional data structure. We apply the quotienting method to represent data points. The binary representation of any data point is partitioned into 4 parts. We name them ST, header, header prime, and body, respectively. The data points are distributed into n over log n sub-data structures according to ST. Therefore, it is unnecessary to explicitly write ST down. To answer a query X, we check if there is a Y in sub-data structure ST of X, such that their suffixes are same. With high probability, every sub-data structure contains O log n data points. So, we focus on designing the sub-data structures which maintains O log n data points. The data points in sub-data structures are grouped into data blocks. A data block is represented by a variant of Elias-Venn encoding. The code word consists of 3 parts. The first part represents the population of the headers. For example, the bit string in the slide means there are 2 data points having header 0. One data point has header 1. 2 data points have header 2. The second part is the concatenation of all header primes. The third part is the concatenation of all bodies. So, to retrieve the case data point in lexicographic order, we retrieve its header from the first part, then retrieve the case header prime and the case body from second and third paths, respectively. The code uses O1 plus log 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 n plus log u over n bits to represent a data point. Recall that the data block contains log n over log log n data points. Thus, the headers and the header primes fit in constant number of words. The critical component of our navigation structure is the compressed tree. Bender et al. Proved that for random data points with high probability, the compressed tree with respect to the data points can be represented in O log n bits. Given a query X with the compressed tree, we may efficiently compute the rank of the only data point which matches with X. An array of pointers is the compressed tree. The case entry of the array is the index of the data block, which contains the data point whose rank is k. So, with the two components, we can immediately find out the data block which maintains the relevant data point. But we still don't know the in-block rank of the relevant data point. On the other hand, we can't retrieve the whole data block. We can fix the issue by two simple observations. With high probability, at most O log n over log log n data points share identical header and header prime with the query X. Pointers corresponding those data points are consecutively stored in the array. Hence, we may retrieve all the pointers corresponding to those data points, then compute the rank of the relevant data point among those data points in the block. For example, assume the headers are B and S. To retrieve X5, we retrieve these pointers, and we find that the pointer corresponding to X5 is the second 2. So, we know that in block 2, they are data points with headers S, and X5 is the second one among these data points. On the other hand, all the headers fit in constant number of words. Given the headers and the rank, we immediately know the in-block rank of the desired data point. Now, the insertion comes. We always put the new data point into the last block and keep the tree updated. The problem is that we can't keep the array of pointers updated. So, how do we retrieve the new data points? We introduce indicators and a buffer. The indicator array is a Boolean string. The values indicate if the data points are in a data block which is under construction. To retrieve a new data point, we scan the indicator array to compute its in-block rank. The buffer is an array of pointers. The case entry is the address of the data point whose in-block rank is k. For example, X8 comes after X7. So the buffer looks like this. To retrieve X7, we compute its in-block rank with the indicators. Then we know that the rank is 2. So X7 is the second data point in the block under construction. Both of the indicators and buffer fit in constant number of words, so we may easily keep them updated. Finally, how to reorganize the data blocks? To reorganize the data block, we have to get these things done. But we can only get the first thing done in constant time. Our strategy is to reorganize the block in the procedure that a new block is being filled. To do so, we introduce a new buffer and a new indicator value. We let 2 denote that the data point is in a block under reorganization. We use a new buffer to maintain the block under reorganization. Hence, we need to add one more thing into the task list to flash the buffer for new insertions. After each insertion, we run the reorganization algorithm for constant steps. The reorganization finishes before the new block becomes full. The reorganization won't bother the query algorithm if all the algorithms are designed carefully. I won't elaborate this part in the talk, but if you are interested, you can refer to our paper for further details. Okay, second part. We show that the membership data structure solves prefix matching under spatial input distribution. The database of prefix matching is a set of strings. Given a query X, we are required to answer if there is a prefix of X in the database. Review our data structure. The way we encode the data block requires that the data points should be long enough, at least log m bits. The tree requires that any data point should be a prefix of a random point, and the database are prefix-free. Now we can summarize. The succinct membership data structure with capacity works for prefix matching if the data points are long enough and the random database is prefix-free. In particular, the data point should be of length more than log m and be a prefix of a random point from the universe. The succinct membership data structure without capacity works for prefix matching if the lengths of insertions are non-decreasing. We deal with short data points with a bitmap. The case entry of the bitmap denotes if there is a prefix of k in the database. Finally, we reduce the filter problem to the prefix matching problem, and it meets all the requirements. Every insertion increases the overall false positive rate. Therefore, we apply the standard double when full method and choose different false positive rate for different data point. We partition n insertions into log n phases. In particular, phase I contributes false positive rate epsilon over I log u. To answer a query X, we query all the log n phases. Check if there is a collision. The mth harmonic number is at most log m. They are at most log u phases, so the overall false positive rate is epsilon, and the redundancy becomes n log u bits. The remaining issue is how to answer the query on all the log n data structures. We observe that we may use one hash function for all the phases. For ith data point, we choose the prefix of the output of the hash function as its avatar. In this way, the problem becomes prefix matching. Then, we observe that the prefix matching meets all the requirements. In conclusion, we present the first succinct filter for sets of unknown sizes. Our data structure enjoys the best of both worlds. The data structure has constant worst-case time for all operations and is space efficient. The key idea is data block. We don't have to store the insertion order. Our data structure solves the problem by reducing it to prefix matching. There are some interesting open problems. It is easy to say that our data structure is not space efficient if epsilon is constant. So, can we close the gap in this regime? To the best of our knowledge, there is no lower bound for dictionary problem for now. So, it is interesting to close the gap for dictionary too. That's all. Thanks for your listening. If you have any concern, please shoot me an email.